Hello everyone, I'm Kumar Abhishek. Today I will present our work titled Designing Truthful Contextual Multi-Bandits based Sponsored Search Auctions. This work is done under the guidance of Shweta Jain and Sujit Gujar. Myself and Professor Sujit is associated with Machine Learning Lab at IIIT Hyderabad, and Professor Shweta is from IT Ropar. Let us start with an example. Usually, when we search for a query, the search engine, say Google, throws a lot of ads to us. Uh, for example, when we search for free-range dog food, we can see a lot of ads. So we are concerned here. We are concerned over how these ads are got selected. Typically, an auction is performed for the selection of the ads which are being displayed. The sponsored search auctions, also known as SSA, plays a major source of income for the search engines. For example, in 2019, Google has ad revenue of around 134 billion US dollars. The it is SSA is different from the traditional ad industry, as the agents pay only when the user clicks on the ad. Uh, Click-through rate is an important parameter which is also defined as the probability of an ad getting clicked. Let's try to understand the dynamics of SSA with a cartoon depiction. Here is an agent or advertiser who want to display his ad on the advertising agency, let's say Center. But the Center has other n-1 requests to display the ad, but n has only one slot to fill. The agent says that he's valuing his ad for BI for a click, but the Center is not sure if the agent is telling truthfully. And as neither of the nor the agent nor the Center is knows the CTR, hence the Center is fixed on the problem of learning CTR while trying to elicit the true valuation before making the decision. So CTRs and bids play an important role. For example, uh, when there are two agents, let's say one having $0.7 bid with CTR 0.8, another with $1 bid and CTR 0.3, we will consider the agent one to be better. Hence, CTRs and bids both play an important role in allocation. But the CTRs are unknown, and the learning of CTRs can be modeled as a multi-arm bandit problem. Uh, and as each advertiser or agent has a private valuation VI associated to the click, which the advertising agency or the Center does not know. The agents bid their valuation at BI, which may or may not be equal to the valuation VI. So here mechanism design is needed to ensure that the agents bid truthfully. Together, the both concepts merge into what we call as multi-arm bandit mechanism design or MAB mechanism design. Let us dive a little into multi-arm bandit. Multi-arm bandit, also known as MAB, provides framework for analyzing sequential decision making while addressing exploitation trade-off. The performance of MAB algorithm is evaluated in terms of regret. The regret is further defined as the difference between cumulative rewards of the algorithm versus the optimal policy with the known rewards. The objective of a MAB algorithm is to minimize regret. In case of a vanilla MAB problem, there are n options or arms, out of which only one is optimal, and the reward distribution is stochastic what is unknown. And the feedback is we consider bandit feedback, where the reward is only observed for the arm that has been pulled or selected. There are t number of total rounds, and at each round an arm IT is selected and a reward RIT is received. There is a very interesting variant of multi-arm bandit known as contextual multi-arm bandit. Let's see an example how it can help. So let's say there are two players who want to buy some tennis equipments. But from the picture we can see one is interested in table tennis and other in lawn tennis. Both of them searches on the search engine for tennis equipment. One of them, but the search engine uh, gives the same result to both of them. With the help of context, we can personalize the result and hence can get more click overall, and hence the more revenue. Uh, the Let's see the state of the art in the non-strategic settings. When extra information or context is available to make decision, learning CTRs has been modeled as a contextual MAB problem or ConMap. Typically, learning in ConMap is more complex than naive MAB. We assume the relation between CTR and context should be linear, which is represented as this. Uh, when the agents are non-strategic, the researchers have addressed the problem of contextual multi-arm bandit and proposed algorithms like LinearCB and sublinearCB. Let's look into the state of the art in strategic settings. Uh, Multi-arm bandit mechanism design has been addressed previously by Babayoff et al., Devanur et al., and Sharma et al., but neither of the works has addressed the contextual variant of the problem. To the best of our knowledge, only Gatti et al. Has addressed the problem of using contextual information in MAB mechanism design problem. Uh, they proposed a deterministic exploration separated mechanism, which we refer to as MREG, and offers strong game theoretic properties. However, they lack many practical challenges. They have many practical challenges. It incurs high cost of learning. Center needs to know the number of rounds for which it needs to execute beforehand, and in some cases, all the rounds could be free. That can be dangerous. So our goal here is to design a non-exploration separated truthful con-map mechanism that learns CTR efficiently, that is minimizes regret, and may not need prior knowledge of T, and obviously does not have free rounds. So we measure the performance of mechanisms with regret. We define context social welfare regret of mechanism as follows. Uh, First, let us highlight previous work. Babayoff et al. Stated and proved a characterization result regarding truthfulness of a MAB mechanism. In this characterization result, they proved and stated that the monotonicity and allocation rule is sufficient condition for truthfulness of mechanism. That is, for example, if we want to design an exposed truthful mechanism, then designing exposed monotone allocation rule is sufficient. They also provided black box procedure to transform exposed monotone allocation rule to exposed truthful mechanism. So from this characterization result, Our problem of designing truthful conmap mechanism now boils down to designing exposed monotone allocation, which learns CTRs efficiently. Summarizing our main results, first, we design an allocation rule, namely ELINUCB-SB, which is an elimination-based exposed monotone algorithm. Next, we design sublinucb-S, which is also exposed monotone algorithm. And finally, we demonstrated the efficacy of both of our mechanism using simulation and established superior performance over the existing literature. ELINUCB has been optimized using batch size. It leads to an exposed incentive compatible mechanism, but in theory can incur high regret. Whereas sublinucb-S we proved to have the worst case regret of O of n square root dt log t. We have designed ELINUCB-SB allocation rule based on LINUCB algorithm, existing LINUCB algorithm. The main idea is balancing exploitation dilemma through elimination process. In this, we initially the agents are selected in round robin order, that is exploration, until the designated agent is eliminated. In that eliminated round, we exploit the agents, which preserves monotonicity while addressing the dilemma. Hence, it is crucial for our mechanism design. It has very interesting features like ELINUCB-SB is exposed monotone. It does not need to know T, hence it is scalable. But the major drawback is theoretically it can incur O of T regret. We designed sublin UCB-S allocation rule based on sublin UCB algorithm. We follow the similar idea as in the previous algorithm, but the change being we keep different available sets for different contexts, which resulted in sublinucb-S being exposed monotone, and the upper bound, and theoretically we were able to attain the upper bound of O of n square root of dt log t. We attribute O of n to be the price of truthfulness. We can attain the truthful mechanism by using the exposed truthful monotone allocation rule, that is ELINUCB-SB and sublinucb-S. Now let's see the experimental results. The here red one represents the AAMAS algorithm mechanism which has been proposed previously. The plot maps regret versus rounds for 7 agents. Due to the unavailability of real world click bids data, we use the synthetic data. We randomly generated theta i's and context x for d is equal to 4, where d is dimension, and generated clicks accordingly. The regret is averaged over 100 iterations for 10 to the power 6 rounds, and we can see from the graph that our proposed mechanisms have outperformed AAMAS by a very large margin. To conclude, we believe our work is the first to design a non-exploration separated conmap mechanism. Although our mechanisms are randomized, they are game theoretically sound and scalable as compared to AAMAS. AAMLINUCB-SB and AAMLINUCB-S outperforms AAMAS in experiments, and theoretically AAM-sublinucb-S matches the regret in non-strategic setting up to factor of O of n, which is the price of truthfulness, better by a factor of t to the power 1 by 3 than that of AAMAS. These are some of the works for the reference. Thank you all for your attention. For any queries, you can write to me this. Thank you.